Okay, hello everyone. This is the Stats 203 class, the graduate level elective titled Large Sample Theory. So this is my first time teaching this class remotely. And also I believe this is my actual first time of teaching a remote class. So this is a great challenge for me. And I hope that the remote teaching will not disturb our learning experience so much. So that's why I want to first maybe have a few minutes to talk with you about how we can make this learning more interactive and effective. So I noticed that all of you are currently muted. That's good because your noise will not disturb others. But I hope some of you, if your environment allows, can turn on your video camera. So at least I can see some of your faces so we can have some sort of interaction. Otherwise, I feel like I will be just like talking to a screen, and that's not good. And also, if I cannot see your facial expression, I will not be able to see whether I'm at a good speed. So my plan is to teach slower than usual for this class this quarter. So just to make sure that we are on the same pace. So yeah, thank you for those of you who showed up. So what I plan to do for today is we'll first go through the key points in the syllabus, and then I would like each of you to briefly introduce yourself so we can see each other, and I can connect your name with your face, and you can also let us know why you decide to choose this class. If you're still shopping around, that's okay, but I hope to see your motivation of taking this class and what you expect to learn. Okay, so let's start. This is the syllabus, and it's already posted to CCLE. So if you just click this link, that can take you to our class every Tuesday and Thursday. And it's every lecture is for 1 hour and 15 minutes. This is the, sorry, I think I need to update this. This is the old one, sorry, my bad. So, but you know the CCLE, right? Once you log in, you will see the class. And tentatively, I set my office hour on Tuesdays at 1 to 2 p.m. using the same Zoom link. And you can also schedule appointments with me if you need. Okay, so what is this course about? This is a graduate course in large sample theory, and it will constitute concepts and results that are central to both theoretical and applied statistics. So I have to say that a lot of the results we will cover in this class have already become standard methods in applied statistics, and you will see how they are useful. Okay, and another name for large sample theory is asymptotic theory. So asymptotic, which I'll explain later, means that your sample size goes to infinity. Under that scenario, how will your statistics behave? Okay, so these are the topics I hope to cover. So these are topics I hope to cover, but I want you to understand that these things are all, so maximum likelihood estimates, like MLE we'll refer to, likelihood ratio test statistic, bootstrap density estimation, and posterior, that's in Bayesian statistics. All those familiar topics have been studied under asymptotics. So you can see, if we want to name one thing that's most crucial to theoretical statistics in like 20 years ago, it will definitely be asymptotic theory. And we will learn the basics in this class. Okay, so in my notes, there are many proofs, but I understand that going through details in proofs will not be so ideal for this remote teaching setting. So therefore, my plan for this quarter, for this class, is trying to be concise, and I will explain the ideas in those proofs, but I'll leave the details for your reading. So if you're interested in understanding how these proofs work, you will read the materials I post. But if you are okay with just applying the theorems and you don't care so much about the proofs, I think that's also allowed for this time. What you can do is to understand the intuition and the ideas of those theorems. So that's what I expect. All right, so the requirement, we will require you to have some mathematical maturity for this class. For example, you need to be quite comfortable with advanced calculus. That's what I would say. And probability theory is also what we'll use frequently. But in our next lecture, we will give you some review of the probability basics we will use throughout this course. Okay, so textbooks. So this is the textbook I'm going to use. So let me see if I can, I can switch my camera so that you can take a look at this book. So I'm actually going to use a combination of my own camera and the projector. So you see, maybe I need to turn off the virtual background. That will make this work. Okay, great. So you see, this is the book I'm going to use. It's called A Course in Large Sample Theory. It was a book published in 1996. And I would say it's a very concise and very classic book if you're interested. So not very thick, you can see. Only, how many pages? Only 200 pages around. So, and every chapter in this book is about one topic we're going to talk about in class. So if I zoom in a little bit more, is it working? Yeah, so you see, if you look at here, not so good. But every chapter, every part is about one topic. And I think this is a very typical book that was written in the old days. That is, the authors clearly know what he was talking about. And so basically every chapter is pretty standalone, even though it depends on the materials of previous ones, but you can treat it as a separate topic. So that's why if you have the access, it will be good to borrow an ebook to read it. I don't understand why this book was so expensive on Amazon. So that's why I would not try to encourage you to really spend the money if you don't have the budget. But this is a really good book, yeah. So that's the basic, that's the most materials will come from here. But don't worry about it if you don't have the book, because I'm going to share the lecture notes anyway. Okay. So, but due to the time limit, we cannot finish this book, to be sure. So that's why if you're really interested in those materials, buying a book or getting a book would be nice. Another thing is this book, 1999 by Lehman. And this one is actually a little easier, I would say. So how this book will work is that it gives you the elements in large sample theory. So you can see that compared to the Ferguson book, and by the way, Ferguson is a UCLA faculty, a retired faculty from the statistics department. So in the old days when we still have access to our lunch, you can see his picture posted in the lunch. So yeah, Ferguson was a very great statistician who made a lot of contribution to theoretical statistics. And Eric Lehman was a professor at UC Berkeley, but he passed away a few years ago. And this element of large sample theory, you can have access to it by using the UCLA VPN. So if you connect the UCLA VPN, you can access this book for free, I think, because it's by Springer. We have purchased other Springer books. So this one gives a lot of elements about what we will use. However, it's not as, I would say, not as rigorous as this Ferguson book. So if you compare the two side by side, you can see what I mean. Okay, so topics. Today, I'm going to talk about the mathematical background to start with, and then we will talk about the probability and what we mean by convergence, right? We'll talk about three types of convergence three types of major convergence. To be exact, is the convergence almost surely, convergence in probability, and convergence in distribution. And the third type is also called convergence in law. And for the third type, the foundation is central limit theorems. So I think many of you have learned this before from an undergraduate class, but this one for here, we're going to treat it more rigorously. Okay, and then specific to the convergence in law, we will cover those results, including the famous Slutsky theorems, and what are the limiting or asymptotic distributions of those statistics, functions of sample moments, sample correlation coefficient, Pearson's chi-square, asymptotic power of the chi-square test, okay? And we'll also talk about the asymptotic distributions of MLE, Fisher information, Cramer-Rao lower bound. That's just the asymptotic result about how good, or it's like how good an estimator would behave, and asymptotic efficiency. So we will also, if we have time, we will talk about the U statistics, statistical functionals, and density estimation. Probably we won't have time for that. But bootstrapping, this is something I want to cover. And also rank statistic, sample quantiles, and extreme order statistic. So those are the things that we use a lot in applications. So for example, a famous rank statistic is median. And also sample quantile is more general than the median. Median is the 50th percentile. And for extreme order statistics, we mean the maximum, the minimum, the second largest, the second minimum, the second smallest. So those statistics are what we mean by extreme order statistics. Okay, so about the expectation or how we evaluate your performance. So we will assign you a bi-weekly homework. So because of this remote teaching, so your homeworks will be submitted to CCLE. So if you have the capacity to type in your answers, because it will involve a lot of math notations using LaTeX, that will definitely be preferred, especially I think for all the PhD students, right, in the statistics department or related quantitative majors, using LaTeX is like a basic. But if this is something new to you and you want to use handwriting, we will also accept that. So just to make sure that when you scan your handwriting, you scan the notes or your writing clearly. So the reader can, the reader who will grade your homework can really see what you write. And so for this final evaluation, we will ask everyone to submit a final paper. And so the final paper is expected to be written independently by every student. And you have the flexibility to choose a topic of your interest related to our class materials. So it doesn't have to be some cutting edge research. For example, if we covered a topic but it's not elaborative and you want to further look into that topic and read some relevant textbooks or old research papers to really clarify a topic, that's also okay. So you have the choice. And our goal is really to help you learn one topic of your choice well by writing this final paper. Okay, so we hope this will be a useful experience for you. And also, I will use this opportunity to help you try to see what academic writing is like. So basically, what I think I will do is that I will post a template about a paper, and you can use that template to write your final paper with similar length and similar style. Okay, so this is my current plan. In our last 1 or 2 lectures, every student will do a very short 5-minute presentation to introduce your chosen topic to the class. And we will also share all your final papers to the class. So for example, if you think a topic identified by a peer is very interesting to you, then you can check that peer's paper. So basically, this presentation is like an advertisement for your chosen topic. And so students can all see what topics others have chosen. Okay, so that's it. And as a graduate level course, I don't think you need to worry too much about the grades, but here is the division. So the majority will be on homework. So that's just based on your attitude, right? If you pay a lot of attention, you cannot do badly in homeworks. And 10%, small proportion for the 5-minute presentation, and another majority is final paper. So that's the evaluation plan. And I think that's it. And we will have one holiday in this quarter. That's Thanksgiving Thursday. Okay. And so please keep a current email address with this myucl.edu because the CCLE announcements will be sent to that email. And if you haven't received my first 2 CCLE announcements, please let me know. So we need to make sure that you're on CCLE, but it should be done automatically once you enroll. Okay. So I think that's all I want to say about the syllabus. And we have 21 of you here. So probably we can take turn to briefly introduce yourselves. And maybe I think the efficient way is that I can use the order that appears in my screen to call your names, and then you can introduce. Okay, so let's start from Ashley. Ashley Chu.
Hi. What information do you need? Just my name, my department, and what else?
So yeah, so a very short introduction you want to about yourself. So how you want others to know, especially me, and also why you want to take this class.
Sure. So as you guys can see, my name is Ashley. I'm a second-year master's student in the stats department. I took actually Professor Lee's course 201B last winter.
Yeah.
And so I really enjoyed that class. I actually thought you were going to be teaching, I think, 205 this quarter, but 203 should
that will be next quarter.
Oh, okay.
Yeah.
But I really enjoyed your teaching style. And separately, this past summer, I did an internship that focused a lot on experimentation. So I wanted to learn a little bit more about sampling theory.
Oh, great. Thank you. Okay, and Syllabus, you're the second on my list. Syllabus 10.
Hi, I'm Syllabus, and I'm a third-year PhD student in the bioinformatics program. My research is pretty much in the system bio, which is a very different direction than statistics. But I think I'm very interested in that statistics part because we also have many data set we try to mine and try to extract some information from that. So this is part of my journey of educating myself more in statistics.
Great, thanks for your interest. And Dongyuan, you're the third.
Hi everyone. I'm Dongyuan. I'm a second-year bioinformatics PhD student, and I'm actually come from Jessica's lab. And my current research is about statistical methods in single-cell sequencing data analysis. Yeah, I think this course will be very helpful for me since asymptotic theory is kind of like one of the most important parts for modern statistical theory framework, and I think I will learn a lot and it will benefit my own research. Thanks.
Oh, thanks, Dongyuan. And Gabriel Roos.
Hi, everybody. My name is Gabriel. I'm a fourth-year stat PhD student. And the reason I chose to take this class is because the topics here are becoming more and more relevant for my own research. So hopefully I can get a better overview than what I have and fill in some of the gaps. And that'll help my research.
Sounds good. And welcome. And so next one is Hedy Shah.
Hi, I'm a second-year math PhD student.
In what major, sorry?
Math, applied math.
Okay.
And I take this course because, I'm interested to some extent.
Okay. Yeah, interest is the most important thing, and thank you. And next one, Ian McGovern.
Hi, I'm Ian. I'm a second-year master's student in the stats department, and I just want to take this course because I took the 200 series and I really liked kind of theoretical aspects of it, and I thought the parts of 200C that sort of talked about things in this course were interesting, so I wanted to learn more.
Great. Okay, Leah Briscoe.
Hi, I'm a fourth-year bioinformatics PhD student. I heard about this class last year from a few friends, and I really liked it, and I think it's really helpful. It comes up a lot in all my other statistics classes so far, and yeah, I just want to learn more.
Thank you. Yeah, that's good to know that we have recommendations from other students. Okay, Melody Huang.
Hi, I'm Melody. I'm a third-year PhD student in stats. My research interests are in causal inference, and asymptotics has sort of continually shown up in the literature, so I thought it would be good to get a more formal understanding of how everything works.
Great. And Ming Tao Xia.
Hello, everyone. I'm Mintal from the math department. I'm a second-year PhD student, and my research direction is applied math and the spectrum methods. I just want to learn more about statistics, so I choose to take this class, but I have not decided it. I definitely
Great.
want to know more about statistics. Thank you.
That's okay. Yeah, so I think shopping around is totally understandable and allowed at this time. Yeah, and also your feedback will also be important. If you think like the speed is not what you're looking for, you can let me know. Okay, Peng Yu Chen.
Hi everyone, this is Pen Yu. I'm a PhD from civil engineering, and but I'm actually also a master's student in stats. I'm actually going to graduate soon, but after taking so many stats course related to machine learning, I think it's a good chance to learn some theory behind it, like Jessica just mentioned, the asymptotic theory. So yeah, that's why I want to enroll this class. Thank you.
Thank you. And Raw Chen, you're showing up here, but I know you're just auditing. Would you like to say something?
Sure. I take this class, I believe, 2 years ago, and I try to refresh my memory and see what I can get from this class again. So my name is Ruochen Jiang. I'm a 5th year PhD student in Jessica's group.
Okay, yeah, so Roger is a keen learner, so he really wants to learn this again. Maybe this is good to know, right? Okay, Samantha, I'm not sure how to pronounce the last name, A-R-U-N, Arun or Aaron, you can correct me.
Hi, my name is Samantha Arun.
Arun, okay.
I'm a PhD student in the Civil and Environmental Engineering department. And
okay.
I've elected statistics as like one of my minor course, like minor fields. So I took this course mainly because I think statistics is cool and everyone should know a little bit of statistics. And yeah, that's why I'm here.
Okay, sounds good. So we have 2 civil engineering students already, right? Peng Yu and Samantha. And next, Wenbing Guo.
Okay. Hello everyone. I'm Wenbing Guo from bioinformatics program, and I'm a 3rd-year PhD student. And I also work with Dr. Jessica Lee, and my current research is try to link the genotype information and also the gene expression. And also at this time, I use a lot of statistical techniques that is related to this asymptotic theory. And yeah, I'm also really interested in this modern stats concepts, and yeah, that's the reason why I take this class. And I also want to learn more stats, and yeah, that's basically for my information. Yeah.
Okay, thank you, Wenbing. Xinyang Li.
Hi everyone, my name is Xin Yang, and I'm a 2nd year master student in biostatistics. And I'd like to learn this course because it's like a foundation of statistics, and it's like a foundation of other applied courses. And my current interest is like in machine learning and data mining. Yeah.
Thank you. Thank you for the introduction and welcome. We have the first biostatistics student here. Yeah. Our next student is Xinyi Guan.
Hi, I'm Xinyi. I'm a 2nd year PhD student majoring in the operations management from the Anderson. Yeah, I took the Stats 205 last quarter, and I think Professor Lee is an excellent lecturer. And that's why I want to take this course. And also, I think I can learn a lot from this course, and this can benefit my research.
Great, good to know. Well, welcome to take my class again.
Thank you.
Okay, next student is Yu Hao Yin.
Hi everyone, I'm Yu Hao Ying, fourth year PhD student in Stats department. My current research is on experiment design. So I'm taking this course for both personal interest and exploring possible future research topics.
I see. So are you working with Professor Xu in our department? Okay, yeah. Welcome. And Zach Siegel. X Siegel.
Hey there, I'm Zach. I'm also in the operations management department in the Anderson School. I'm a second year student as well. I am taking this class because I took some of hierarchical linear models last
year. The 205.
Yeah, and I was taking too many classes, but I'm going to take it next quarter, and I liked the amount that I was in it, and I thought this would be a nice way to have more classes from the same in the same style, so that I could have a deeper understanding.
Yeah, also good to know. Yeah, and also thanks for taking my class again. I think I should say this to many of you in this class. Okay, our last student to be introduced, Zihan Liu.
Hi everyone, this is Zihan Liu, and I'm a second year PhD student in civil and environment engineering. And my major is geotechnical and earthquake engineering. And my research interest is like system reliability assessment. So I would like to learn some statistic basic stuffs from this stats course. Yeah, thank you.
Thank you. I like your virtual background. It's such a good advertisement for UCLA.
Yeah, thank you.
Yeah, so did you make this yourself or you get it somewhere?
No, I think the chancellor sent the email to us, providing the background. Yeah.
I see. You know, this is also something I can actually show off to my friends or my relatives. I can say that, okay, since I joined UCLA in 2013, and UCLA has surpassed UC Berkeley for a consecutive number of years, right, recently. That's really proud of us.
Yeah.
Although I graduated from Berkeley, so I should pity it, but you know, I should adore my current institution. Okay, so thank you all for the introduction. I believe we have more students enrolled in this class from the roster I can see on my UCLA, but because I think due to time zone differences, those technical issues, we may not have all of them at this real-time lectures. So it's most of us here, but I will post the recording. So if they miss the real-time lecture, they can watch the recording. But I don't think you will feel like you waste more time here, because I feel like this interaction will be very essential. And also I would like you to raise questions whenever you have it. So maybe the most efficient way is that you just unmute yourself and ask the question. So you don't need to raise your hand, because sometimes I will not be able to see it, right? So you just unmute yourself and ask the question like we do in a regular classroom. Okay, so that's the introduction of the class and the introduction of yourselves. So this is let me count. I think this is my 4th time teaching this class. So I think I must have improved in some way. So hopefully I can explain things in a more clear way than before as I teach more and more, right? I think 205 is like an example as well. I taught that for multiple times, and I can clearly say that I did better later. Okay, so I shared the lecture notes to CCLE. So you should have a copy of that on your computer. And after every lecture, I will make corrections to the notes and post a refined one. But I don't think it's a good idea to really go through those line by line on my computer screen. I think that's too inefficient. And also the text is too dense out there. And I also don't want to use slides for teaching this class, because you know the details are the key. So if I use slides, once we turn the slide, you will not be able to see the previous pages, so you will easily get lost in the process. So that's why the best solution, in my opinion, was to use a projector I purchased for teaching this class, so that at least we are sort of like using a blackboard as we used before. So let me stop sharing this PDF, the syllabus, and I'm going to share the screen of this. Let me see. This software is called a visualizer. So this one. So can you see it well? Let me see. I need to pull up your faces so I can see. Okay, so let me see where I can see you. I can no longer see you anymore. Once I started, okay, yes, I can turn it on. So can you see this visualizer app? Okay, great. So what I think I will use is pen and paper to write here. So hopefully the resolution would be okay. Do you think it's too big, or can you see it well? Maybe I can pull up the visualizer again and adjust the resolution a little bit. Yeah, this is our first lecture, so we have to really tune these things up. Okay, this is already the highest resolution. Maybe it's the focus, but let me continue writing and see how it works. Okay, so let's start. Today we're going to talk about the math background. So let me see, okay. Is it a little vague, right? Or does it look clear to you?
It is extremely vague.
Yeah. I think menu focus, can we do it? That's weird. So actually, Dongyuan, because we were using this yesterday, right? So do you think yesterday was better?
Yeah, I think yesterday is better than current view. So I'm not sure what happened.
Yeah, I'm not sure what happened either. But let me see if I can. Oh, I got it. Because I was zooming too much just now. It's still vague, right?
Yeah, I don't think we can read it.
Yeah, I don't think so. So let me try to adjust the resolution. Is it better?
Yeah, I think currently it's better.
Right, can you see it clearly? Can you actually at least, maybe I can continue.
Yeah,
Okay.
I think we can recognize it, but it's kind of like still a little bit vague,
Yeah.
but much better than previous one.
Much better, right? So, okay, now I zoomed in. Is it better?
Yeah.
Okay. Okay, so we'll see. If it's not working well, then we will find another approach, but we'll just try this for today. Okay, so we'll talk about the math background. So as I said, so when we talk about large sample, we are actually referring to this n. And this n is the what we call the sample size. Oh, another suggestion, which I also posted to CCLE, is that I hope to learn this class well. You can write together with me, because I think that's just, for me at least, when I was a student, I think writing while listening to lectures is a good way for me to understand better, rather than just sitting there and listening. Because if I just sit there and listen, sometimes I may get distracted or bored, right? But if I'm doing something, then that makes my learning more active. And I see some of you are actually doing that. That's good. So this is the sample size. And by sample size, we actually mean, more specifically, is the number of observations in our data. Like if we're trying to study human population, or we're trying to predict election result, the number of observations is the number of individuals in our sample. So large sample really means that n is large. Okay, so we're interested in, when n is large, how our statistics will behave. And why is this important? Because you see, ultimately, if we let n go to infinity, and that's what we call asymptotics. When we let n go to infinity, we are basically capturing the whole population. Our sample becomes the population, right? Then that behavior is the optimal behavior we can get using statistics. So therefore, the behavior of our statistic when sample size large is a way for us to probe into the population based on our sample. And that's the optimality we could aim to achieve if our sample is large enough. Okay, so then when n is infinity, we have no excuse to say our sample is too small, so we are not doing well. We cannot say that. So that's why you can think about asymptotics as an ideal in our statistical learning. Okay, so therefore, you see, we are trying to study this increasing sequence of n, right? So you will see later, we will have this idea later in the class. We will often use this notation, xn, or sometimes we use tn, or sometimes we will use sn. But no matter which math notation we use, they are all statistics based on of a sample of size n. In other words, this subindex n indicates the sample size. And we are interested in how the statistic change with sample size. And we all know that statistic is itself a random variable, right? So they are all random variables. So I will use this notation RV to stand for random variables. And then there are two layers of changes. One is the increase of n. So we have x1, x2, x3, x4 to x infinity. Another layer of change is the randomness of each xi in the sequence. So therefore, for today, we want to start from the simple thing. Let's first look at, let's first consider this xn to be fixed. So we just ignore the randomness of each statistic. We consider as a constant, but still we get a series. And let's call that an. So, you know, in mathematical statistics, when we use lowercase notations like a, b, c, d, those are referring to constants. And if we talk about random variables, we often use capitalized x, y, z, s, t. So you see, capitalization suggests random variables, and lowercase notation suggests fixed constants. Okay, so let's talk about that. So the first concept I'm going to talk about is about limit, right? So you see, given a sequence, and let's say about this, we can call this a sequence, right? And let this n start from 1 and goes to infinity. This is what we call a sequence. If you still recall your calculus class, when we talk about a sequence, we are often interested in its limit. That is what it becomes as n goes to infinity. So here we are going to give you the formal definition of a limit. So I don't know how many of you have learned this, but this is the fundamental definition of limit. And I'm going to give you some intuition about it for this class. So limit means what? So what the sequence is converging to, and we call the point that it converges to, if it does, right? We call that limit. So therefore, this discussion is considering it's conditional on the existence of a limit. So for example, we can write it in two ways. These two ways are equivalent. The first way is that we write an, right arrow a, as n goes to infinity. So we say that this is an goes to a as n goes to infinity. And this is what we use more often in statistics. So this is a common notation in statistics. But I know when you took a calculus class in mathematics, we often see that limit notation. That is, we write the limit of n goes to infinity, that the limit of an is a. So these two things are equivalent. It's just that in statistics, we use the top one a little more common. Okay, then how do we mathematically define this limit, right? So what do we mean by the limit? So here is the most important definition, what we call the epsilon delta definition. So what does that mean? It's like a refreshment, okay? I think many of you must have learned this before. So here we use epsilon as a neighborhood size. Is a neighborhood size around the limit A. Okay, and we use here is a sequence, or I shouldn't say epsilon delta, I should say epsilon n. And we use n, let me say n0 epsilon as an order in the sequence. So when we say the sequence converges to limit A, what do we mean exactly? It means that no matter how small the neighborhood size is, we can always find that our later sequence will be contained in this neighborhood. So in other words, we can shrink our neighborhood size gradually, that no matter how small it is, as long as we go far enough into our sequence, we can always find that later numbers in the sequence are contained in this neighborhood, and that's limit. Okay, so mathematically we write, so the math definition, we can write it as for any, so I'll use the notation, this is for any epsilon greater than 0. So just for my writing simplicity, I will use this notation. And there exists, and this is the notation for there exists. There exists an n0 that is depending on the epsilon. Okay, so n0 is actually depending on the epsilon, such that ST stands for such that we have a n minus a, the absolute difference, the distance between a n and a. So we know that we are on the one dimension. Okay, so I should say that this is a one-dimensional sequence. So probably to make it easier for us, we just say these are real numbers. So we're under the one-dimensional case. The distance between a n and a is always less than epsilon for all the a, for all the n that is larger than this n0 epsilon. So this is the mathematical way of writing what I just said before, right? No matter how small the neighborhood size epsilon is, as long as we can always find the point on order in the sequence so that all the numbers after this order is contained in the neighborhood of A with size epsilon. That's the definition of limit. Okay, so on the other hand, we can talk about this is about convergence. On the other hand, we can talk about divergence, right? Then what does divergence mean? Divergence basically means that we're still having a limit, but here the limit becomes infinity. So the sequence number becomes larger and larger and larger. Then we can think about a similar definition, right? How can we define that mathematically? So previously, we are talking about a neighborhood around A. And for divergence, we can talk about an upper bound on the sequence. So we can say that no matter how large the upper bound is, you can always find an order in the sequence so that all the later numbers in the sequence are greater than the upper bound. If we can always do that, then we have divergence. So mathematically, I can write it as, okay, so for any m greater than 0, and no matter how large this m is, there exists n0 that depends on m, such that we have this an greater than m for all n greater than n0. Okay, so that's what we mean by divergence. So we can always increase our upper bound, and still, no matter how large the upper bound is, we can always find a later subsequence that's above the upper bound. Okay, so with those two things, why do we want to define this, right? This is like calculus. The reason we want to define this is because here we're going to talk about the relationship between two sequences. And that's the key thing to give us a starting point. So the relationships
between two sequences, we call them AN and BN. So let me give you some intuition of this. So here in asymptotic theory or large sample statistics, what we care mostly about is how our test statistic or statistic sequence, the XN, I talked about before, right? So we care about this thing, this XN, and how it changes with N. But often the formula of XN written out in N can be very complex. It can be a very complicated math formula. So therefore, we want to find a surrogate, a simpler formula, but the order of that new statistic and how it changes with N should roughly be the same as our XN. So in other words, we try to find what we will define later, an embedding sequence, so that we can use that simpler sequence to replace our current or our original sequence, so that our mathematical analysis will all be based on that simpler sequence. But in order to do that, we need to make sure the two sequences are similar enough. And how do we define similarity? Here it comes. We need to define their relationships. Okay, so before we talk about random variable sequences, we start with the fixed variable sequences, AN and BN. They are constant. Okay, the first relationship we want to define is what we call asymptotic. So I will use this short writings to stand for asymptotic equivalence. So this is what we often write for equivalence. So what do we mean? And the notation for this is AN twiggle BN. Okay, and what do I mean exactly? The definition of this is actually very straightforward based on limit. That is, the ratio AN over BN converges to 0 as N goes to infinity. That's what we mean by asymptotic equivalence. Okay, so you see, if the two things share the same limit, then we can simply say when we want to study AN asymptotically, we may just want to study BN as a surrogate. And what is an example of this asymptotic equivalence? Let me give you some examples. So let me ask you a question. So if I have AN defined as N plus N squared, and I have BN defined as N. Okay, then my question is, are they asymptotically equivalent? Think about it, and you can unmute yourself if you want to give an answer. Yeah, Zach, I see that you're shaking your head, right?
Yeah, because the ratio AN over BN does not approach 1, it approaches infinity.
Exactly, right? Yeah, correct, no. How about this? So if I change BN to N squared, will your answer change? Right, and Ian, you're nodding your head, right? So you think it's yes.
Yeah,
correct.
yeah. AN over BN will converge to 1.
Exactly. So you see, so if this is an increasing sequence with N, right? So basically the intuition here is that if AN and BN are both increasing sequences, we look for their dominant term and see if the dominant term is of the same order. So here the dominant term is N squared, and here's N squared. They are of the same order, right? And also for asymptotic equivalence, we need to care about constants. So for example, if I change BN further to 2N squared, will your answer change? Right. Here, if we still do the ratio, then we can see the limit will become 1/2 instead of 1. So in this case, they are still not asymptotic equivalent. Okay. So a similar definition, let's continue. A similar definition is what we call same order.
you can consider this to be a little more general than asymptotic equivalence. And for same order, we use this notation. I don't know how to call it, but this is how we write it. Okay? So it's no longer trivial anymore. And how do we define same order? So same order basically is about this. So it's defined as, okay, asymptotically, this thing, AN over BN ratio, we take the absolute value. So what we want to say is that asymptotically, this absolute ratio is bounded. Is bounded asymptotically. So in other words, we're not going to require there's a limit, but we want to require that this ratios converge to something not infinity, not negative, not positive infinity. That's it. So mathematically, we can write the definition as, so for any, so what we want to say is that, so there exists, so there exists m, lowercase m and big case m. Both are positive and both are not infinity, both are finite, and integer and 0, such that we have this ratio, absolute ratio AN over BN absolute value, bounded between lower m and upper m for all n greater than n 0. So you see here, we're not talking about limit. We're just talking about a bound, right? And for this bound, what we mean is that as long as we can find one bound, like a set of m, lower m and big M, given that set of bounds, if we can contain our sequence, our later sequence, subsequence in that bound, we can say asymptotically the ratio is bounded. That's what we mean. Okay, so therefore you see, obviously, asymptotic equivalence is a special case of the same order, and same order is more general. So let's come back to the previous example, okay? So I want to say is that if we have asymptotic equivalence, then for sure we have same order, okay? But the other way around doesn't hold. Same order is more general. So for that, for example, you see that example we previously killed, this one, AN is this, and BN is 2n squared, right? If we talk about asymptotic equivalence, they're not. But if we talk about same order, then they're yes. Okay. That's same order. And I have to say, in statistics, mostly we don't care so much about constants. So same order is good enough, right? We don't usually aim for asymptotic equivalence. That's too stringent and not really necessary because the constant is not random. Okay, and two relationships is what we called small o. Okay, small o, we write it as AN is small o of BN. So when we write this, what do we actually mean? So the definition of this is about limit. Sorry, I should cancel this part. So what I'm saying. Oh yeah, I think that's right. My bad. It's equivalent to that AN over BN is convergent to 0 as n goes to infinity. Okay, so whenever, what I mean is that AN grows slowly, more slowly than BN does, then we say AN is a small o of BN. And it's defined based on limit. And sometimes we say that it depends on what we actually mean, right? So if in statistics, let's think about the relation. So if AN is some prediction error or estimation error that we hope to go down to 0 as n go to infinity. And Bn is another sequence that go down to 0 as n go to infinity. So in this case, you can see that what Bn essentially offers is like a conservative bound on An, because Bn grows more slowly, right? An grows faster. I think I said it the wrong way. The An grows faster, goes down to 0 faster. Bn goes down to 0 more slowly. Then we have this. And then you see, we can say Bn is a conservative rate estimate for the convergence rate of An. And that's often good enough, because people, if they see, okay, your conservative rate is already fast enough, then we're happy. Okay, so let's look at an example of what we actually mean. This is a very famous example. I think some of you have heard me talk about this in my other classes. It's the bias-variance trade-off in statistical learning, right? So if you recall, what this says is that if we talk about the mean squared error of an estimator, so it can be decomposed into two terms, the square of the bias and the variance. So I'm not going to talk about the detail behind this relationship, but if you're not familiar with this, just check. You can easily find the exact definition by Google. Okay, so here we can talk about a very typical estimator, and this is in the notes. It's about the Bayes estimator of a beta it's the Bayes estimator of a beta parameter. So basically, I'm going to say this, so I should write it. So it's actually X follows binomial N and P, okay? N is the number of draws, P is the success probability, and I'm going Bayesian, so P, I assume it has a beta prior A and B. So combining those two things, I get a Bayes estimator and I can call it P hat, and the notation is a little different from the lecture notes, but I think the P hat is what we often use more often. So this one has the formula A plus X divided by A plus B plus N. So in other words, a Bayes estimator is a combination of the prior and the MLE. Okay, the MLE here will be X divided by N, and we have some information from prior. But what I want to talk about this is because we look at the bias and the variance of this estimator, we will see that, so I'm just going to write it down. So the bias of this P hat will have the form as, you can check the notes for the detail, A minus B times P over A plus B plus N. That's the bias. And the variance of this P hat will have the form N times P times Q divided by A plus B plus N squared. Okay, then based on our definition of same order, right here, you see you can regard the bias as a series that goes down to 0 as n goes to infinity. Variance is another series like our Bn, which also goes down to 0 as n goes to infinity. Then my question is the bias and the variance, are they on the same order, in the same order, given this formula? Peng Yu, you are nodding your head. Right, they are. Right? They're both on the order of 1 over n. So you see, based on our notation of the same order, so we can say that here, this bias is of the order of 1 over n. And this variance is also of the order 1 over n. And so they are of the same order. But if we come back to this variance bias trade-off, you see, here we need to square the bias
but keep the variance, then which one, their bias or variance, will dominate the MSE? Which one?
The variance.
The variance, correct, because we are going to square the bias, right? When we square the bias, its convergence rate to 0 will be faster, but the variance rate will be slower. So the slower rate in this convergence to 0, the slower one will dominate the MSE. So the MSE is dominated by variance. And why do we care about this? Right? So this is regarding the efficiency of our statistics or our estimator. And efficiency is usually defined by MSE. So if you see that variance is the dominating term, and if you want to find an estimator that has the overall MSE, overall smallest MSE, then you should focus on reducing the variance while the bias may not matter so much. That's why sometimes we can accept biased estimators because we know those estimators have smaller variances. So we desire their variances at the price of their bias. Okay, that's it. And but this is not really related to the small o, right? So we need to connect to the small o. So what I'm going to say is that here we can write the bias square is a small o of variance, right? Because that satisfies this definition. The bias square is converging to 0 faster than the variance does. So it's small. And last relationship. So I think you can check the lemma. Sorry, before we go to last relationship, lemma 1.6. That's about some properties of the small o relation. But I think these are all very obvious. So I'm going to skip it. So properties of small o. Yeah, to check them and just make sure you can prove them using this simple definition, and it shouldn't be of difficulty. And oh, one more thing, actually, I should say, before I move to big O. So there are some examples typical examples we often use when we talk about relations. So those typical examples.
Professor, can you move your paper up on the screen?
Yeah, sorry. Yeah,
Thank you so much.
Thank you for letting me know. Yeah, sometimes I just forgot. Thank you. Yeah, so typical examples. I'm going to give 3. So the first one is for those polynomial series. So that we have an as n to the power alpha, and bn is n to the power beta, right? And then we say, for this case, an is small o of bm if and only if alpha is less than beta. That's the first relationship. How do we compare two polynomial series? Or geometric series. These two are often used equivalently. And the second thing is regarding polynomial versus exponential. So whenever we have this, let's say, an, we write as n to the power k with k positive. And we also have bn written as a to the power n with a greater than 1. So in this case, we always have an is small o of bn. In other words, for those increasing series, exponential growth is always faster than polynomial growth. We know that. So this is the intuition behind why we desire those compound interest, right? When we do investment, that's so important. And the third thing is regarding polynomial growth versus logarithmic growth. So in this case, if we have an as log n, and the log can have any basis, and we have bm that is equal to n to the power k. Okay, and so this k must be positive. Then we would always have
an small o of bn. In other words, logarithmic growth is always slower than polynomial growth. So those are the examples we will often use. All right, so last relation, right? So we talk about asymptotic equivalence, same order, small o. Now we come to big O. So I'll write it very big so that you can see the difference. So for this big O, you can see the simple way, and we write it, right? We write the notation as an of big O bn. So you can think about it as a combination. I'll just say it's a small o and same order. So you can think about it just as a union of those two relationships. So no matter whether the relationship is small o or is the same order, we can call them big O. Okay, so basically when we write this thing, we can actually say that, so basically, let me just say it. So for example, let's say we have this an equals to, or maybe I should give you an example, right? So we can say that an is equal to n, and bn is equal to n squared. So in this case, can I say an is big O of bn? Based on the definition, is it small o or is it same order?
No, it's not.
It's not. Why is that?
It's not small o, and I mean clearly, and then it's not the same order since it converges to.
Why is it not small?
Oh wait, did I mess it up?
Actually, small o is defined as the ratio an over bn is convergent to 0 as n go to infinity.
Oh, sorry, I was thinking the other way around.
Yeah, that's okay. Yeah, sometimes we got confused. Yeah, exactly. So it's small. So it's a small o, so that's why this is yes. Okay, then how about I change it to an is n squared and bn is still n squared. Is it still big O? Yes, yeah, because this is same order and asymptotically equivalent. Okay, further, how about an goes to n cubic and bn stays as n squared? Is it still big O? No more, because here we see if we do an over bn, that ratio, absolute value will converge to infinity. It's not bounded. So this is no. So what does big O mean? Did you get intuition? The big O, you can consider it as an asymptotic upper bound. So in other words, what it actually means is that if you take the ratio of an over bn and take the absolute value, then that absolute ratio will be asymptotically bounded from infinity. Okay, that's big O. So then essentially bn offers an asymptotic upper bound on an. Okay, so I'm going to write this. And also the reason I want to use the projector and notes and paper is that after the lecture, I can scan my note and send it to CCLE. So I think that's more convenient, better than using iPad. Okay, so I want to say that an is big O of bn is essentially means that bn is an asymptotic upper bound on an. That's the intuition behind this notation. Okay, so that's pretty much it about the relations. And then later, so we're now at fixed sequences, right? So later, when we go from AN to XN, so when we talk about for random variable sequences, so let's say XN and YN, so no longer constant sequences, then we will change everything from small o to small op, big O to big OP. So we'll have those. So we will have small op and big OP. And it's still the same statement, but here the P stands for with high probability. Okay, and you have seen this a lot in those statistical methodology papers. So here they are trying to use those asymptotic arguments, but because they're dealing with random variables instead of fixed variables. So therefore they have to talk about with high probability. So what does it exactly mean? Let me give you examples. So for example, XN, we write XN is small op YN. Then what this means is that we have XN. What this means is that we have the probability that XN over YN, okay, is less than epsilon. So I should put here. So for any epsilon greater than 0, this is still the neighborhood size. The neighborhood size around the limit 0, because we want this O, small o, to be xn and yn converges down to 0, right? So the limit is 0. And we have any epsilon greater than 0. So for this epsilon, we have that this probability that this ratio is in the neighborhood. This is in the neighborhood with high probability. And this high probability will be some value that depends on, let me write it here, will be some value that depends on, I'll use lower p, depends on n, and depends on epsilon. Okay, so basically what we need for this term is that we want P and E increases as epsilon decreases. Okay, let me see if that's right. So epsilon is the neighborhood size. We want this to be, oh, sorry, I think I made it wrong. So we want this P and epsilon to be decreasing as epsilon decreasing. And also we want P and epsilon to decrease as n, yep, we want this to do it better, right? So to increase, my bad, to increase as n increase. That's what we desire for this small op. So basically, we want to say if we have a larger sample size, or we go later into the sequence, then this random ratio is going to be more likely within the neighborhood. So that's why this probability of being in the neighborhood is going to increase. So we're actually giving a lower bound on this probability. So P and epsilon is a lower bound on this neighborhood probability. And we want the lower bound to increase as n goes larger. And in statistics, the intuition is that as our sample size becomes larger, we are getting better by using yn to approximate xn. So this thing is going to be within that neighborhood of 0, more likely with higher probability. On the other hand, how this lower bound probability will change with epsilon? That should be, as we decrease the neighborhood size, it becomes more and more difficult for this ratio to be in the neighborhood. So that's why this probability will decrease. So these two things, so basically if you see somebody showing this result and claim lowercase small op, this is something you should check.
right? So for example, I'm just giving you intuition for checking people's talks if you listen to seminar talks. So if this relation doesn't hold, then there must be something wrong in the derivation, because this is the intuition we need to have for this result. Okay. One more thing. How about big OP? So if we have this, then we're saying that this is essentially an asymptotic upper bound. So Yn is an asymptotic upper bound on Xn with high probability. The P stands for high probability. So we would have the probability that Xm over Yn is controlled by some upper bound here. And this is for any n greater than 0. For any upper bound, the probability that this is controlled from the upper bound, that means it's protected from infinity. This thing would also be greater than some lower bound we call P n capital M. So the same argument would apply. So as M goes up, as the upper bound goes up, what happens? As the upper bound goes up, it's more easy for this ratio to be under the upper bound, right? So therefore, the lower probability bound should go up. And also, as n goes up, we are doing better and better. So this ratio should be better controlled under the upper bound. So this lower probability bound will also go up. So these things will guarantee that we are having the high probability control. So high probability is guaranteed by this lower bound, and it should be some value pretty large. It's a probability, so it should be close to 1. Okay, so these are the intuition behind what we call small OP and big OP. But in order to thoroughly understand those two things, today we're going to just understand small o and big O for fixed variable sequences as a starting point. Okay, so that's pretty much it. I only got to explain a very small portion of the lecture 1. So I will expect you to read the remainders for those background reading. And the next class when we start, so we're running a little out of time. Next class when we start, we will talk about a very important definition, the quantile of a distribution, because we're going to use that. Okay, and then we're going to move to lecture 2 about the convergence, 3 types of convergence. All right, so if you have any feedback about the speed and about the quality of this remote teaching, you can send me an email and let me know. So if we have any issues, we'll try to do better next time. So see you next Tuesday. And we're not going to post our first homework until next Thursday. So for now, I think it's a good time for you. If you have time, it's a good time to really do those background reading to get you prepared for this class. Okay, thank you all for your cooperation and see you next Tuesday. Bye.
Thank you.
And I'll post the YouTube video. So the YouTube video link will also be posted to CCLE. So you should be able to see it there. Okay, bye and have a good day.
Thank you.
Thank you.